Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. I'm Wolfram Schulte. I'm currently hosting Victor Kulyamin. It's my pleasure to host him for today's talk on the practice of standards of formalization. I met Victor at various testing conferences, and I was in general impressed by the breadth of work that they are doing, from testing open standards, and that's what we will hear today. He's actually part of the Institute for Systems Programming, which has probably more than 20 people working on testing various aspects, from hardware to mobile devices to browsers, and he will mainly report on testing things in the Linux context. So I look forward to your talk. Thanks for joining us, Victor.
Thank you for invitation. I actually was in doubt how to focus my presentation, because actually we do a lot of work in these directions and it is very wide. So I'll try to provide some brief overview of this work, and then to speak more detailedly about some little part of it concerning testing mathematical libraries in Linux or in Unix systems as a whole. So first I will talk about background of our institute concerning, of course, with testing. One of the first big projects performed in our institute was development of regression test suite for real-time operating system, switch operating system for NARTL networks. And since that, we continue to perform projects related with testing of operating systems from different sources. We conduct such testing for a real-time operating system developed in Russia, which is also POSIX compatible and used in some defense applications, as far as I know. We conduct test development for Linux standard base, and we also developed a conformance test suite for a Ring 653 standard, which is a standard on process management, time management, and partitioning in real-time operating systems in avionics. We also have some background in compiler testing. Most notable are the projects related with a description of static semantics for further development of conformance test suite for C and Java languages performed in 2002-2004, and a project on testing optimizing units in Intel compilers, where the main problem was that Intel can generate a lot of tests, gigabytes of tests, but they were very poorly targeted at optimizing units. So they need some tests that execute the code of optimizing units, but were designed as general programs and provided on input on the compiler as a whole. So we succeeded in doing this, and actually reported, to my mind, about a dozen of bugs in Intel compilers as the result of this project. Then we also have background in protocol testing, started from testing Microsoft Research implementation of IPv6 protocol, then development of test suite for mobile IPv6, also for Microsoft Windows CE. And then we also developed test suite for IP security protocol. And this project is now in proceeding. It is not finished yet. And one of the latest additions to our profile is hardware testing. We participate in development test suites for MIPS-based general-purpose microprocessors with some DSP extensions. So this is the general background, what kind of projects we perform. And now about technologies we used. We mostly focused on model-based testing and static analysis technologies. And in model-based testing, we developed a so-called Quest technology, which was used for testing Nortel Networks operating system. And further, it was rebranded in UniTESK technology, which is continuously developed by adding some extensions in different application domains. The general scheme of model-based testing, as I may recall for the audience, is the following. We have some system under test, and we have some model of its behavior on the basis of which we should construct test coverage criteria for further testing. Then from the behavior model we can automatically produce test oracles that evaluate results of our testing, and maybe some model of state of the system under test for more precise evaluation and also for tracking coverage more specifically. And from the coverage criteria, we automatically produce some coverage metric to measure adequacy of our tests. Then we also construct some test generator, which can use all these modules to perform testing and to perform immediate evaluation of its adequacy. This is the most general scheme, maybe, that can be refined and simplified in different places. For example, we can skip Oracle and provide just testing results for further evaluation by people. Or we can skip on the fly test execution and just generate tests for further testing. Or we can leave out state model to generate tests only on the basis of some coverage criteria used. Actually, all these variants are used in different contexts and in different projects in our institute. Then one of the main activities of our institute in the last 5 years is participation in Linux standardization. It is all concerned with a lot of different distributions and versions of Linux. As far as I know, there are more than 500 officially registered different distributions of Linux. And the main problem, of course, how to provide applications for all these distributions. Do we need different applications, different development for each of these distributions? Of course, if we need to do so, it will be very hard. So one of the proposed solutions for this problem is Linux standard base, which is binary interface standard, which supposes that we can simply move applications between different distributions conforming to the standards without any recompilation, just in binary form. If we use the same hardware platforms as a base. So it was supported on, to my mind, 9 or 8 different hardware platforms. And for each hardware platform, it defined a set of binary interfaces which provide such interoperability between different distributions. This standard includes a lot of more specific standards like POSIX or XOpen or OpenGL, and it also includes a lot of de facto standard libraries used in many Linux applications like libxml or Qt and so on. And not only C language libraries, but also GDK and Perl libraries, and for widely used programming languages. For example, for C language, it now consists of about 40,000 functions, which are not specified in some uniform way. About 2,000 functions, which mostly comes from POSIX or XOpen standards, are described more accurately and more precisely, and other functions are not so well defined, and some of them have no any documentation at all. Some of them have, for example, one line of description. This function do something, and that's all. So if we need to check conformance to such a standard, of course, it is a problem, and it is a hard task. And what we perform in relation to this Linux standard-based activity. Institute actually is responsible for LSB infrastructure development, and this infrastructure includes standard database which has data on all the libraries, operations, standardized on their use in different distributions, on tests already developed for them. This infrastructure also includes conformance checking tools both for distributions and for applications. And for distributions, these tools are based on static analysis and testing, and for applications on testing again and on monitoring or dynamic verification. We also develop information system for LSB evolution, which supports analytical activities concerning making decision on further development of the standard. For example, how to evaluate which libraries are widely used in different applications and which are not. And also, we perform a project on Linux driver verification, which is based on the technology very similar to the one developed in Microsoft Research and now used in static driver verifier, to my mind, in Microsoft. And we use BLAST tool, very similar to SLAM. But also we have some additional instrumentation based on some aspect-oriented things, so that we can define a model of a system and the model of a driver in non-invasive way near the code of a driver. Now, if we have such a huge number of interfaces, how we can test them? Actually, we cannot do it with the same accuracy. And for 2,000 functions which are described rather accurately, we provide conformance testing on the base of UniTESK technology. For less strictly but nevertheless well-defined functions, we provide some manual test development augmented with some support for requirement traceability, for parameterized testing, for example. So some things are automated, but the main decisions are performed by people in this test development. And for other functions, we used specialized massive automated test construction technology, which is based on the information already stored in the standard database. This database has information on function signatures, data types of their parameters and results. And this technology is based on the idea to refine information on data types, to put in this database some additional information on how such a data type can be correctly initialized and can be finalized. And then some exploration tool just constructs tests on the base on this information, just puts some initialization procedures to construct parameters, and then some call to the tested function, and then some finalization. Actually, of course, these tests are not accurate and not good, but they provide just some testing that we can do for such a great number of functions. Before that, they have no tests at all. Maybe some words very short about UniTESK test development technology. It is
what, are you presenting the findings of your testing efforts as well? So how many bugs, how great the variety between the different Linux distributions is? So
I see.
The results of your findings?
Actually, there are different kinds of findings. First kind is some inaccuracies and issues in standards themselves. For example, we reported about 2 or 3 dozen issues to POSIX team, and these issues were accepted by them. And we have, to my mind, just about the same number unreported issues on POSIX standard. Also, there are, to my mind, hundreds of various issues in various distributions and libraries, about 2 or 3 dozens problems in glibc library, which also are accepted. And actually, about 50, to my mind, or 60 defects in other widely used libraries on Linux. And concerning differences between distributions, actually there are differences, but they are not reported as some specific issue. Usually they are concerned with some use of different versions of libraries, or some in some distribution you may use some patch, in some distributions you may not use it, and something like that. So usually if we find such issues, we transform it into a report on some bug in library or issue related with usage of patches for some library. Actually, most of such issues found are published on our site, linuxtesting.org. Okay, several words about UniTESK technology. It is based on the idea of so-called stateful contracts, when we define behavior of a closely related group of operations in terms of its model state and pre- and post-conditions of these operations. Then we can use structure of postcondition as a source of coverage criteria, because in most practical cases, postcondition is not a single predicate and consists of a lot of different ifs, and each of these ifs can be considered as coverage goal. Then we perform some coverage targeted abstraction of state to construct a finite state machine of a group, and perform on the fly exploration of constructed finite state machine to obtain testing. I wish to be more specific on the testing of math libraries, because it also illustrates some aspects of formalization of standards and some issues you can find on this way. So if you pose a question how one can test implementation of mathematical functions, first of all, you need to look at the existing standards that describe requirements to implementation, to these implementations. There are 4 of such standards with slightly different coverage, because, for example, IEEE 754 provides requirements only on some basic arithmetic operations. And actually, these standards also provide slightly different, not consistent set of requirements. So, to recall some details of floating point arithmetic, floating point number type is specified by 2 integers, the number of bits used as a whole for this number, and the number of bits used for exponent. And if the exponent is not consists of all zeros or all units, it is so-called normal floating point number, and can be calculated by this formula. If the exponent consists of all zeros, it is the normal number, and it is calculated by slightly different formula. And you may note that there are such a net effect as -0 in floating point numbers. Actually, IEEE standard tries to not to distinguish 0 and -0, but in some specific cases there are differences, and they are directly specified in this standard. And also, if the exponent consists of all units, the corresponding number is an exceptional number, which may represent infinity, also called not a number at all, nan, which is used to represent results that cannot be correctly stated as finite or infinite. So, the main floating point types has the following parameters, and in addition, this IEEE 754 standard provides the following requirements on computations. It describes behavior of basic arithmetic operations, square root functions, fused multiplication additions, and some type conversions also. In many cases, the result of computations cannot be represented as exact floating point numbers. In this case, you should somehow round the exact result to a number. And for this purpose, this standard defines 4 different rounding modes, which prescribe the direction of rounding in each case. It also provides restrictions on
to the nearest, aren't there 2 cases? It's right in between to either go towards 0 or go to the even. thought there were 5 modes.
What? I don't understand.
You were saying there are 4 rounding modes.
Yes.
I'm familiar with 5, but maybe the 5th one is not IEEE 754. And so the 5th one, I believe, splits the to the nearest in 2 cases. Because to the nearest doesn't mean anything if it's precisely between 2 things.
I see. Yes, sometimes the 5th mode is mentioned, but in the standard there is only 1 to the nearest mode, and it says that if the exact result is just in the middle between 2 floating point numbers, then we should round it to the number which with more zeros on the end. In addition, this standard also provides requirements concerning cases where these operations should return nans or infinite results, mostly naturally. And it also specifies 5 flags that can be set in case of some exceptions to signal about some incorrectness in computations or some specific situations occurred. If you consider C language standard and POSIX standard, they provide some requirements to library functions implementing various mathematical functions. And they mostly try to extend IEEE requirements to these functions. For example, they specify exact values in some points for these functions. They specify that in points where these functions should be infinite, we should set this division by 0 flag, and they also specify situations when nan results and invalid flag should be set. Besides that, POSIX also provides some specific requirements. For example, it says that if the function is equivalent to its argument in the neighborhood of 0, then for the normal arguments, it should return the argument. This is in contradiction with rounding modes, because this requirement is applied for every rounding modes. So it is not a formal contradiction, because IEEE standard do not say anything on such functions, but it is in contradiction with some extension of IEEE requirements you may imagine. Another example of such, not a contradiction, but maybe inconsistency between POSIX approach and IEEE approach, is requirements on values that should be returned in case of overflow. POSIX again requires that one and the same value should be returned independently on the rounding mode, and also it said nothing about specific value of this constant. Actually, different libraries use different values, and this is the obvious source of non-interoperability between implementations of mathematical functions. So if you provide some calculations on one platform and have such results, then they can be incorrectly interpreted on the other platform with another value of this constant. One more example of such inconsistency between POSIX and IEEE is POSIX requirements that sometimes some functions should return non-nan results on nan arguments. For example, maximum of nan and any number should be equal to this number, not nan as it would be if we try to extend IEEE policy on nans. So these standards are not in good correspondence. You can also look at the full requirements of POSIX for sign functions, and here some general descriptions and some requirements on return values in some specific situations. And you can note that there are no any words about inaccuracies or precision of calculations. So any function which does this and provide any other values can be considered as correct implementation of sign function. There is so-called standard on language-independent arithmetics, which is mostly strict standard on mathematical libraries, and it provides rather accurate set of requirements starting from preservation of sign of mathematical function by its implementation, preservation of monotonicity, boundaries on inaccuracies. It is also specified that these boundaries and these restrictions can be applied to trigonometric functions only for small arguments where the period is much larger than the distance between neighbor floating point numbers, because outside of this interval they became just a pseudo-random set of points. And also this standard provides restrictions on symmetries of implementation, on exact values, and on some asymptotics near zero usually, because near zero the density of floating point numbers is much higher. And also some restrictions on inequality relations between such functions as exponential and exponential -1, or hyperparabolic cosine and sine function, so on. So if we look at the whole list of requirements from different standards, we can note that the single requirement to perform correct rounding of exact results according to current rounding model is sufficient to infer most of them. Actually, this requirement is very good for standardization because it provides the best computational accuracy you can achieve. All the issues in applications using mathematical libraries related with inaccuracies should be then investigated as properties of algorithms used, not as related with accuracies of libraries themselves. It also provides perfect interoperability between different libraries and applications. You can get the same results from different implementations if all of them implement this requirement. And also it is sometimes considered as rather hard to implement, there are examples where it is achieved. For example, CR-libm library implemented in RIA tries to implement correct rounding for all elementary functions. And Intel implementation of glibc libraries for Linux on Itanium platform do not achieve this, but come very close. They actually provide for most functions only 1 ULP or 2 ULP errors. So when we try to construct tests, we base them on this requirement of correct rounding. we also tried to extend naturally the ideas of IEEE standard, because it is basic for floating point computations, and to extract the corresponding requirements on non-results, infinite results, and exception flags for all the set of mathematical functions. Then, after we can say what we can check, what we should check with our test, the next thing to define is what data we should use. For testing mathematical functions, we use three sources of data. First, it is bit structure of floating point numbers, which actually defines some natural boundaries like 0, infinity, the largest positive number, and so on. And also can be used to construct numbers corresponding to some patterns of mantissa, which usually became a source of some subtle errors in different implementations. For example, very well-known Pentium division bug was related with some specific pattern of mantissa of arguments. Also, we found, for example, such bug in glibc implementation of integer rounding function. It also is related with such pattern of bit structure. Two other sources of test data are intervals of uniform behavior of a function and points where it is rather hard to calculate correct result, because it requires more precision than in average. So,
what do you mean by uniform behavior?
I will explain on this slide this. By uniform behavior, I mean intervals where the function preserves sign or kind of monotonicity, or it has some nice asymptotics just on this interval. So actually all the numbers can be partitioned in some set of intervals according to these ideas, specific for a function, of course. And even for functions of several arguments, the same idea is working. You can partition now not an axis, but all the plane or a space into a set of areas where the function has slightly different behaviors. And
what is the typical number of the errors?
It depends. For some functions like square root or exponential, there are 10 dozen intervals. For functions like trigonometric sines and cosine, there are millions of intervals, but not all of them can be chosen for testing. Actually, for such complex function, we perform some additional filtering of these intervals, trying to look only at intervals where the behavior is mostly specific. For example, we try to look at the periods of sign where it comes most closely to 1, to the value of 1, or to -1, or to 0. So actually, I will say some words about this later. Actually, from all the periods of sine function, for example, we choose several thousands of such periods which contain some specific behavior, and use them as such intervals. Then the third source is so-called hard points, where the exact result of a function lies, for example, very close to the mean between two consecutive floating point numbers, so that we need very precise computation to make correct rounding of this result. The same picture can be observed when we using so-called directed rounding modes to 0 or to infinities, but the pattern of the results, here you can see the pattern of the function result, which is close to the mean between the mean of two floating point numbers. And for directed rounding modes, the pattern is slightly different. Here, this result should be close to some exact floating point number. And there are some examples of these hard points. For example, you can see here in this point, the correct rounding of tangent value can be performed only if we calculate additional 80 bits, additional to the average mantissa. So maybe such points are very rare. To answer this question, we can evaluate their number on the basis of a simple probabilistic model, which occurs to be very close to reality. It says that if we look for points where number of additional bits needed for correct rounding is less than the number of bits in mantissa, then we can usually find such points. And their number is growing with diminishing of number of additional bits, of course. And in some general situation, you can see that the numbers prescribed by this model are in very good correspondence with real numbers of such hard points for sine function, for example. But sometimes this model doesn't work because, for example, function can have very good asymptotics. It come close to some floating point number, and each point on this interval became hard from this point of view. But actually, we do not interested in such point as a good test cases, because in such intervals the function can be calculated easily with the help of these asymptotics. So we are interested mostly in isolated hard points, which are not lying in intervals of asymptotics. So there are several methods to calculate such hard points. Of course, we can just try to search them by brute force, and this method works, but only on single precision, where we have just 2 to the power 32 numbers. There are additional methods, such as method based on continued fractions, which allows to calculate some hard points for trigonometric function starting from continued fraction expansion of pi, which gives rational approximations to pi, and also floating point numbers which are very close to integer multiples of pi. Other method, so-called dyadic method, can be used to calculate hard points for square root function. It is based on calculating square roots on modular increasing powers of 2. And so this sequence provides a dyadic square root from some parameter, and for each such parameter, which can be taken as a small odd number, we can calculate usually several hard points with the help of this method. Other methods are based on the idea that hard points correspond to the nodes in the grid of floating point numbers, which lies very close to the graph of a function. The reduced search method used linear approximation of a function and then some optimized search of these nodes close to the line segment obtained. Then lattice reduction is more complex. It uses polynomial approximation and some construction of a space of polynomials, of multiple variable polynomials, which can be then reduced to the basis which gives such close points. Some details of this method are rather intricate. Then I propose a so-called integer seconds method based on the idea that if we have a point where the linear term of a tangent is integer or rational, then the intersections of the graph and the seconds parallel to this tangent will correspond to such hard points. And these intersections can be effectively calculated on the base on reverse expansion series of the difference between the graph and the tangent. So, with the help of all these methods, we computed some set of hard points. Actually, for simple cases like square root, we have calculated all hard points of some badness, requiring more than, for example, 48 additional bits to calculate exact value. And using these results and other sources of test data, we composed test suites for almost all real variable POSIX functions. Test suites are constructed rather simply. There are a framework which performs test execution and comparison between expected result and actual result. And there are a set of test data consisting of arguments and expected results. Expected results are calculated with the help of multi-precision Maple tool or MPFR library. So we use different sources to escape some systematic bugs in both implementations. And here are some statistics of test suites developed. So, for example, these points are some boundary points such as 0, infinity, maximum positive floating point number, and so on. These points correspond to different intervals. These are different mantissa patterns. These are hard points where we can calculate it. For example, for logarithmic gamma functions, it is hard. I don't know effective way to calculate hard points for such a function just now. And sometimes we use other sources. For example, for square root functions, there are a lot of floating point numbers from which square root should be exact floating point number. And they provide also useful test cases. And for sine, logarithmic gamma, and Bessel functions, also the points which are closest to zeros and to extremes are used as test cases. So we composed a huge set of tests for mathematical functions and executed it on several platforms. And that's the summary of details. Here, rows correspond to different functions and columns correspond to different functions, and rows correspond to different platforms. And each cell for each function is divided into 4 parts corresponding to 4 rounding modes. So you can see that sometimes a function performs almost uniformly in different rounding modes, and sometimes it is exact in rounding to nearest and very buggy in other rounding modes. Very implementation dependent. And there are also some examples of bugs found in this testing. Here, bugs related with exponential function and hyperbolic functions. You can see this negative exponentials or exponential of a negative number which is greater than 1 and so on. The same picture can be seen on trigonometric number functions. And for error functions, the same. Error function is some probability, and here you can see that this probability is very high. So the most notable are 2 things to my mind here, that on these 4 platforms, implementation is almost exact or exact in the rounding to nearest and very buggy in other modes. So I think it is because of some optimization performed just for the nearest mode. And also, as I have noted already, implementation of glibc library for Itanium platform seems to be the least buggy implementation under consideration. The other picture shows which implementations provide different or the same results on our test set. So implementations in this colored in the same color provide just the same results on test, and implementations with white cells provide different from each other results. So
White means unique.
yes, all white cells are unique implementations which are not similar to any other. So you can see that if, for example, we consider development of mathematical modeling applications on the base of grid systems or cloud computing, and if we want to use different platforms as a base of this cloud computing system or grid, we can have problems if we automatically arrange or provide some automatic scheduling of calculations on different platforms, because we can get just different results from such applications. And actually, as I know, such scenarios already implemented. In one institute in Moscow, some grid system was developed with some automatical scheduling of computations, and they suddenly faced with different results caused just by different scheduling of computations on different platforms. It was independent team, so they do not know about our results, but you can see that this has practical significance. So some maybe obvious conclusion that formalization of standards can uncover numerous issues, even in rather major industrial standards like POSIX, which has a long history of development and considered as very good in industry. And also, in some cases, formalization is not only ineffective in terms of cost and effort required, but even impossible if a standard has actually nothing to require from some interface. So that's all. Thank you for attention. And of course, if you want to discuss some issues concerning not mathematical testing, but other things I sketched before, you are welcomed.
Victor is here for the remaining week, so if you want to catch him to get some of the issues worked on, then feel free. He's sitting next to in my hallway. That's it this way. And you can take questions. Yes.
Right. So these routines were defined in the Linux library, right?
Not only in Linux, we also here tested implementations of C runtime library of Visual Studio, because it provides almost the same set of functions, except of some.
Okay, so I was going to ask, what about the Intel? I mean, Intel provided some library like this, right?
Yes. For example, this implementation of glibc on Itanium was developed entirely by Intel. And also there are Intel libraries for Windows, which I also performed tests on, but I have not put yet the results in the table. And it seems that the implementation on Windows is also very good. It demonstrates almost the same results as on Itanium.
Thanks again, Victor.